Assalamualaikum and hi to all esteemed panels. I am Shafiq Hafiz from AS245. Today I will present regarding my final year project entitled The Synthesis of Zinc Oxide Nanorods Using Different Pandan Concentration as the Stabilizer in the Seed Layer. My supervisor is Associate Professor Dr. Zuraida Binti Kusaimi. As for the introduction, according to Oxford Learner's Dictionary 2020, nanotechnology can be defined as technological branch that plays with structures that are commonly less than 100 nanometers long, in which scientists use individual molecules of substances to create these structures. Nanofabrication can be done via two approaches, which are top-down and bottom-up, which in this final year project, bottom-up approach was used, where nanostructures are synthesized on a glass substrate, stacking them by layer until they give rise to crystalline. Asif et al. 2019 mentioned that various methods have been introduced to synthesizing oxide nanoparticles such as solvothermal, hydrothermal, precipitation, microemulsion, sol gel, and others. The zinc oxide nanoparticles possess unique properties due to the small size and large surface area, structural stability, high melting temperature, high capacity, high diffusion, and high surface energy. Musavi and Harris 2020. Moving on to the role of seed layer. It is mainly to supply and behave as a nucleation center in order to prevent interfacial mismatch between zinc oxide and substrate. The seed layer will help to lead an epithelial growth process so that the synthesized zinc oxide is well aligned and provide electrons movement in the thin film, a continuous transport pathway, Asif et al. 2019. Different properties of seed layer, such as thickness, will lead to different morphology of zinc oxide synthesis. Problem statement. The use of hexamethylene tetraamine (HMTA), urea, and sodium hydroxide as stabilizer is not a green method, which is not an environmentally friendly. The methods from previous study uses harsh conditions such as high temperature and pressure. As for the significance of study, the green synthesis approach is simpler and eco-friendly compared to the one that uses HMTA as stabilizer. Different concentrations of plant stabilizer in the seed layer will result in different outcomes. As for the objectives, the first one is to synthesize zinc oxide nanorods using Pandanus amarylifolius by solution immersion method on zinc oxide seed layer thin film. Second is to characterize zinc oxide using FISM, EDX, UV spectroscopy, and XRD. And lastly, to analyze the effects of seed layer properties using different pandan extract concentration. Literature review. These are some of the papers that I've used as a guidance throughout my final year project. Moving on to the next part, which is the methodology. There are 7 steps in synthesizing zinc oxide nanorods, which is the first one is preparations of glass substrate. Second is preparation of pandan extract, which consists of 3, 6, and 9% weight per volume. The third one is the preparation of zinc oxide solution, where 20 ml of 3, 6, and 9% pandan extract was added with ratio 1 to 1 with zinc nitrate hexahydrate solution. It was then followed by the preparation of zinc oxide seed layer by spin coating method. I'll explain later regarding this. Followed by preparation of zinc oxide precursor for immersion solution. Then preparation of zinc oxide nanorods by immersion. And finally, characterization using FISM, EDX, UVVs, and XRD. Preparations of zinc oxide via seed layer via spin coating. Zinc oxide solution was deposited onto glass substrate, which rotating at 3000 round per minute. Within 30 seconds, 10 drops were deposited onto the glass substrate, followed by drying at 150 degrees Celsius for 10 minutes for each layer. The deposition step was continued until 5 layers was achieved, and then the glass substrate was annealed in furnace at 450 degrees Celsius for 1 hour. Preparation of zinc oxide nanorods by immersion. The coated glass substrate just now were placed in a centrifuge tube separately. Then 40 ml of zinc oxide precursor solution was added into the centrifuge tube. Then it was sealed and immersed in hot water bath at 90 degrees Celsius for 4 hours. After 4 hours, the glass substrate will rinse carefully with deionized water and anneal at 400 degrees Celsius for 1 hour. Characterization. At XRD, it is mainly to determine the structural properties, while UVVs is to determine the optical properties of zinc oxide nanoparticles. FISM is to analyze the morphology, and EDX to analyze the elemental composition of zinc oxide nanoparticles. However, if FISM and EDX analysis was not able to be done due to Malaysia's Movement Control Order, MCO. Result and discussion. The first one is XRD analysis. Figure 1 shows the XRD pattern of zinc oxide nanorods on glass substrate with absence of seed layer. The peaks observed at 2 theta angle of 31.75, 34.42, and 36.25, consistent to the 100, 002, and 101 crystallographic planes of zinc oxide, Kim et al. 2014. The sample revealed a sharp and strong peak at 002, which is represent a high degree of crystallinity. The 002 peak can be seen as the dominant peak, which is the nanostructure grows preferentially perpendicular to the glass substrate. It can be said that the sample is pure as no other peak was occurred in the XRD pattern. In addition, by using Debye-Jerez equation, crystallite size was calculated to be 53.60 nanometer. Figure 2 shows the XRD pattern of zinc oxide nanorods on Pandan seed layer of 3, 6, and 9%. The peak observed at 2 theta of 31.76, 34.41, and 36.25 at crystallographic planes of zinc oxide 100, 002, and 101. For all concentration, 002 peak can be seen as the dominant peak once again, which is they are highly dense nanostructured synthesized, Ake et al. 2020. 100 and 101 peak in all figure A, B, C indicates that the zinc oxide synthesized were flower-like shape. This may be due to the excess concentration of zinc nitride hexahydrate precursor used. By using the Debye-Jerez equation, the crystallite size of ABC were 52.62 nanometer, 55.66, and 30.88 nanometer. To compare the crystallite size of figure 2C and figure 1, the crystallite size will decrease from 53 nanometer to 30 nanometer, which the Pandan stabilizer in the seed layer helps to reduce the size of zinc oxide nanorods. Next is the UV visible spectroscopy. Figure 3 shows the UV-based absorbance of zinc oxide nanorods on Pandan seed layer of 0 to 9% weight per volume. Figure 3a exhibits the lowest absorbance, proof that seed layer does give effects to the growth of zinc oxide nanorods. This may be due to lack of nucleation center which on the substrate, which helps to prevent the interfacial layer mismatch, Bunyamin et al. 2021. In order to compare the absorbance at wavelength of 375 nanometer, which is the zinc oxide excitation wavelength, figure 4 was plotted, which can be seen that blank sample has a contracting value compared to 3, 6, and 9% weight per volume Pandan extract. 9% weight per volume Pandan extract possesses the highest absorbance of value of 0.4217 arbitrary unit. The presence of Pandan as the stabilizer in the seed layer shown about 30 to 31% of improvement in UV absorbance as compared to the no stabilizer. Therefore, it can be concluded that the increment of concentration of stabilizer resulting in an increment of absorbance value. Transmittance. As the absorbance is 0, transmittance will be 100% and vice versa. They are inversely proportional. From figure 5a, it exhibits the highest percent transmittance, which align with the absorbance shown in figure 3a. The excitation peak of zinc oxide occur at nearly 375 nanometer, which they are bent downward a little bit. From figure 5d, it exhibits the lowest transmittance due to the highest absorbance value shown just now. Next is the FISEM analysis of zinc oxide nanoparticles from different stabilizer. FISEM main purpose is to study the morphology of nanoparticles, but however, due to MCO, FISEM and EDX analysis could not be run. Therefore, the discussion of result will be based on research papers. From figure 6 and 7, the stabilizers used were HMTA, Pandan extract, and Hylocereus undatus. When Ake et al. 2020 uses HMTA, the zinc oxide results in spherical shape and agglomeration with crystallite size of 30.54 nanometer, while using Pandan, it results in spherical shape and agglomeration but lower crystallite size of 24.15. However, Vishnu Priya et al. 2020 uses Hylocereus undatus, and the zinc oxide synthesized results in spherical shape and crystallite size of 70 nanometer. In comparisons between Ake et al. Using HMTA and Pandan, the phytochemical compounds in plant extract helps to reduce the size of the zinc oxide nanoparticles. Next is the EDX analysis of zinc oxide nanoparticles. The determination of elemental composition in the sample can be done or can be analyzed using EDX. From figure 10, the signal of zinc and oxygen appeared indicating the formation of zinc oxide. Chlorine excitation peak may be contributed by excess of phyto compound in the Hylocereus undatus food pill extract itself. From figure 11, zinc and oxygen element had atomic percentage of 38 and 60% respectively. Other elements of weight percent less than 4% were the same as in the jujube fruit. Conclusion. First is zinc oxide nanorods were successfully synthesized on the seed layer. The presence of phytochemical compound in plant stabilizers helps to reduce the particle size. All of the maximum wavelength in UVB spectrum of zinc oxide were between 370 380 nanometer. 9% weight per volume pandan extract possess the highest absorbance of 0.4217 arbitrary unit. XRD pattern showed intense peak at 002 for all samples. In addition, the zinc oxide growth perpendicular to the glass substrate, and they were pure and hexagonal mosaic structure. Moreover, 9% weight per volume pandan extract has the smallest crystalline size of 30.88 nanometer, which is the most dense of them all. It can be concluded that 9% weight per volume is the optimum concentration for synthesis of zinc oxide nanoparticles. The result for FISEM and EDX analysis of zinc oxide nanoparticles was not able to be run due to MCO. Therefore, it was discussed using research papers from other studies. As per the recommendation for this research, the quality of zinc oxide nanorods or nanostructure can be improvised by altering the drying process of pandan leaf, such as air dried, sun dried, and freeze dried. The effect of pH of the zinc oxide solution for immersion method can also be investigated further. Further investigation needs to be done to determine whether 12% weight per volume pandan extract or above produce a better quality of zinc oxide nanorods or not. Characterization of zinc oxide nanorods can also be done with Fourier transform infrared spectroscopy, FTIR, along with Raman spectroscopy. These are my references. I've come to the end of my presentation, and with that, thank you very much.